Hello and welcome to Chapter 6 of Earth History for Philadelphia University. I'm going to be covering the second half of the chapter, and depending on time, maybe get in Chapter 7. So we've talked a lot already about plate tectonics, right? We've talked about all the plates that are out there, the way they move, how they move. We've talked about ocean and continental crust, the different collisions they can have, divergent, convergent plate boundaries, strike slip, transform, things along those lines. Um, as a quick recap, the convection cells that go on in the asthenosphere, the mantle, that not only produce the crust, but also move it, giving us the topography that we have and the organization of the continents that we have. The most obvious examples of this, as I've discussed already, are edges of ocean and continent, North America, Europe, or South America, Africa, being classic examples of plate tectonics. South America and Africa moving away from each other. The fact that they looked like they were once together was part of the reason Alfred Wegener came up with the idea of continental drift. And the center of the Atlantic Ocean is something that we call the Mid-Atlantic Ridge, which is essentially an active volcanic zone that runs literally the entirety of the Atlantic Ocean. And this is pushing the west side west and the east side east, more or less, right? And again, here, if you can look, the west part of Africa and the east part of South America clipped together like puzzle pieces. Why? Because they were once clipped together like puzzle pieces. But I'm not going to stay too long on this. Just want to do a quick recap of the chapter to this point. We talked about these are the various different oceanic things that can happen, but Mid-Atlantic Ridge system, right? This is under the ocean. The ocean's deep. I don't often go to the bottom of the Atlantic Ocean to hang out. This is something that you can't necessarily actively see. However, this particular Mid-Atlantic Ridge system is not the only active tectonic plate zone. Specifically, it's not the only active tectonic divergent plate zone or spreading center. That's not the only one. We have, fun enough, one in Africa. On the eastern side here at the Horn of Africa, we have three different plates, the Namibian plate, Somalian plate, and Arabian plate, all pulling apart from each other in different directions. So much so that the Arabian plate you see is moving northeast, the Somalian plate's moving west-southwest, and the Namibian plate, east-southeast, the Namibian plate is moving west-northwest. This is Terry, if you can imagine, this is, let's say, I can't think of anything off the top of my head for an example, but you have three people fighting over, let's say, a shirt, right? All three people want this shirt, pulling in different directions. Maybe you did physics in high school, you did these force calculations. What happens at this point? All three of these plates are moving apart. The center part here, what's lined out in the red, this is all literally cracking and being drawn away. The Ethiopian highlands here are literally being pulled apart. The continent is being ripped apart by this motion. What's cool about that, I'm going to skip ahead a little bit to the picture, is you get stuff like this. Active tectonic zones creating brand new continental crust where you have this polar part, where you're having these continents dividing. What's going on in this picture is what's going on in the bottom of the Atlantic Ocean. And in fact, this pulling apart, let's take the Namibia and the Somali plates as an example. This pulling apart of an east-west direction is very synonymous, is very similar to what happened between North America, Europe, and South America, Africa, many millions of years ago. Atlantic Ocean once was not there. These pieces right here in Africa and South America clipped together like puzzle pieces. And then over time, the plates that Africa and South America rode on drifted east and west of each other, causing this rift system, causing the Atlantic Ocean to quite literally form. And that is exactly what's going on right here. The Red Sea is being opened up. The Gulf of Aden is being opened up. And all of this area here on the Horn of Africa is being ripped open, forming literally a new sea. Africa is being cleft in half. That's really cool. I mean, yeah, I teach this class, but there's certain things about geology that are always interesting, right? Volcanoes are always going to be cool. The immense power and the immense spectacle and the immense danger of a volcano, you can't help but think that's awesome, right? And just picture the amount of force, the amount of energy, and the amount of magma and lava that is literally ripping a continent off like a piece of string cheese just being ripped off the continent. That's what's going on here. Yeah. Taking that in here, we can talk about other plate boundaries that exist. This is a divergent plate boundary. We also have what we call convergent plate boundaries. Convergent plate boundaries, ooh, my internet connection's unstable. If I blip out, sorry about that. I'll try to get us back on. Divergent plate boundaries are this pulling apart. Convergent plate boundaries would be a pushing together, where we at? A pushing together like this. This plate boundaries are converging, coming together with one another. And unsurprisingly, we have two different types of crust. Each of those can have a convergent zone, and each of those zones has unique things that happen because of it. What happens when two continents together slide together? What happens when a continent and ocean come together? What happens when two ocean plates come together, right? I'll go into a bit of details here, but again, geology is something that you can, the way you imagine it works is probably the way it actually worked, right? If you imagine two chunks of continent collide into each other, what do you think is going to happen? Well, they're going to beat each other up, right? They're going to crumble up. Take a pair of bricks and smash them into each other. What happens? They get crushed up, they get crumbled. Eventually, what we kind of find out is you get mountain forming events there, right? What happens if you take a brick, a continental brick, and ram it into a piece of jello? An ocean crust. Jello is not a good example of that, but you get ram it into something smaller and something more dense. So jello is a terrible example. What you end up getting is, right, the ocean's going to fall underneath the continent. Exactly what you think would happen is, cool enough, what happens? Convergent boundary smashed together. Divergent boundary pulled apart. Converge, diverge. Transform is the example we get wherein the plates are not moving relative to each other. They're moving, well, not relative to each other. Essentially, this is instead of going towards or away, they're going side by side, up and down. So put your hands together, move your left hand up towards the ceiling, your right hand down towards the ground. There you go. That's a transformed plate boundary. And if you notice, if you do that real fast, if you rub your hands together, rub your fingers together like that real fast, what happens? The fingers that are touching get nice and warm, right? That's exactly what happens to transformed plate boundary. Just instead of two different hands, stick them together, or actually, if you can imagine gluing your hands together, flat, put your hands flat, glue them together, pull them apart. Eventually, if you get enough force in there, you can break the glue, right? There you go. You start an earthquake. That is a transformed boundaries. They happen on ocean, and continent. They tend not to happen on continent, ocean, although I'm sure that does happen and is possible. But ocean, continent are the more interesting ones. Nope, I skipped ahead a bit. There we go. Cool. Different types of plate boundaries. Let's go back a bit. Let's discuss a tectonic plate, what it is, and the anatomy of it. The tectonic plate, first of all, has a segment of the lithosphere on it. What is the lithosphere, you ask? Good question. Let's pull it back here. The lithosphere, as shown on this diagram here, represents the crust, essentially. It's the crust and what the crust sits on top of. The crust is the gray part, and the mantle here is this orange to amber, burnt amber color, maybe? I don't quite know. That'd be brown almost. All this right here, this is the mantle, and this gray is the crust. But we consider the lithosphere to be the crust and the top of the mantle. We call that the lithosphere, right? And the idea behind that is that's your solid, firm foundation. That is your rock, essentially. And then that, funny enough, floats on what we call the asthenosphere. The asthenosphere, as shown here, is this orange, well, like orange, like fruit orange colored section. This really thick chunk has a malleable, as I've said before, malleable plastic feel to it. It, in essence, is not melted rock, if that makes sense. I'm sure you're well aware that if you play with a hot glue gun, for example, when the glue comes out, it's still pretty solid to hold a form, but it's very much not solidified yet. That would probably be a good analogy off the top of my head for the asthenosphere. It is solid, but it's also fluid. I think I used in class a couple of times maple syrup, right? Those are all analogies. If you reach down in the asthenosphere, it's not going to feel like maple syrup. It's tougher than that. But the point is that it can flow, that it can move. So if we have that lithosphere, that hard chunk floating on top of the asthenosphere, right? This is your macaroni and water analogy here. If the asthenosphere has some motion to it, has some flow to it, the lithosphere is going to ride on top of it like a piece of macaroni on boiling water. The thing that you find is that when you have these plates, such as this plate right here, there is a current under this plate in the asthenosphere. Somalia, part of Ethiopia and sections of Kenya are all sitting on essentially a piece of macaroni that is just riding the currents. And that Kenya, Eastern Ethiopia, Somalia is still connected because it's all rock to West Ethiopia, South Sudan, Uganda, places like that. So we run into an issue where South Sudan, Western Ethiopia, Uganda, and Sudan proper all want to ride west, whereas Somalia and East Ethiopia want to ride east. And you can walk across this, right? This is all rock right here. This is still connected. It's glued together. But below that rocky crust, you do have a separation there. That separation is caused by, many different things. Could have been created separately. The separation could have been eroded away by the asthenosphere, whatever version you want to go with for the time, right? So these are floating away, pulling away. They're becoming unstuck essentially by the force of the convection. What we would consider to be a very slow rate, 1 to 16 centimeters per year. 16 is cruising fast, I'll mind you. Usually these things move 3 to 4 centimeters a year. And that's something that we can measure. You can go Google it, GPS locations of continents. You can see how fast these continents move. It is remarkably amazing to think that where you're sitting in class next year, you are 4 or 5 centimeters over, right? Your butt is half of a butt cheek to the side in one direction. And then from your freshman year to your graduation, you've moved, what would that be, 20 centimeters? You've moved, heck, half a seat over, right? I mean, 20 centimeters, that's almost the width of a seat that you sit on. If you're sitting in rows after 6-8 years, if you say you go get a master's at a university, you come back, the seat you sat on when you were a freshman is an entire seat away from where you're sitting now. That's kind of ridiculous. And remember, I'm not talking seats here, I'm talking continents. America is about a lecture seat more west than it was 8-10 years ago. And that varies from continent to continent. But again, these analogies are part of what makes this cool, right? So, why do plates move? Why is all this happening? We talked a lot about this picture, about this convection cell. I discussed a lot about the idea of picture a boiling pot of water, some macaroni on it, that all the macaroni is moving. Well, where's the heat coming from? In order for the water to roll and boil, you need a heat source, the stovetop, right? Well, that's where convection comes in. Convection we define as upward and downward flow, and is a response to changes in density from heating and cooling. Essentially, this is exactly what happens, why water rolls when it boils. As things get hotter, they get less dense, right? They get lighter. Gas is lighter than water. So when the water gets hot enough that wants to turn to gas, it loses it loses some density and it floats up to the top. Denser things drop, right? Oil sits below water. You can't mix water and oil. It's a common trait. This works the same for rocks that it does for liquids. In this case, we have a convection of the mantle, that plastic fluid-like asthenosphere that sits below the crust. Within that, we have what are called mantle plumes. Plume referring to coming up, expanding, right? We had plutonic rock before when we talked about igneous rocks, and this is essentially rising columns of hot mantle rock within the mantle itself. A mantle plume would be this upward motion here. Remember, we're going to consider this ocean crust to be the Atlantic. What we have here is you have a plume of hot mantle material coming up to the surface and expelling out. Right? Literal volcanoes coming from the mantle, dragging the plates along with them as they float. Interestingly enough, that mantle plume, we think, can come from as far as very deep down, close to the core, but that's not the only place it comes up. I'm sure you know about the Hawaiian Islands. Hawaiian Islands are not on a zone. Where's that one map? Here we go. Hawaiian Islands do not fall on one of these fault zones, do they? Hawaiian Islands are way out here, I think, right? This is Hawaiian Islands. They're nowhere near a fault zone. You get all this tectonic activity. Iceland, full of volcanoes, right? The Horn of Africa, very tectonically active. But what about out here, Hawaii? Not near any particular. Actually, no, Hawaii's up here. There we go. Not near any particular fault zone. Well, that's where we come into the concept of a mantle hotspot. The mantle plumes, they develop from deep inside the earth, near again, if the earth's an apple, you're talking near the seeds, near the core of the earth. That's where these mantle plumes originate from. Hotspots work a bit differently. Or actually, I should, before I go forward, better, more zoomed in example of this magma flow, magma rising that I'm talking about here, right? Way down here in the bottom, below all this, you have the Earth's core. Earth's core is supplying heat. That heat warms up this magma. As it warms, it becomes less dense by definition, rises up, pops out of the mid-Atlantic ridge, a spreading center. When it does that, the definition means all this material is flowing in this direction. So you have flow in this direction. What does that mean? The mantle that's not necessarily rising is going to be circulating around it, right? This mantle is going to be circulating this way, and this mantle is going to be circulating that way. Again, picture boiling water. It's the exact concept. So what happens when you have the flow of this magma that's not necessarily rising? Well, this is the conveyor belt method that takes this crust here and moves it in the direction of the flow of that magma plume, right? You have this particular side of the ocean rolling one direction and this opposite side of the ocean rolling the other direction. What happens here? This oceanic crust, this limestone looks like, hits this granitic crust, hits this continental crust. Look at the size difference between that blue and this gray here. This guy is going to be sucked down because it's not going to jump on top. It's too short. It has to go below. So this is going to flow it, pull this down, and then what we have here, right? Now we can finally come back to this picture. You can pick and you can imagine, if you will, where did this lava start out, right? This lava's path, this lava's journey is, to call it intense would be an understatement. The journey this lava has taken, how many thousands of kilometers it's traveled to peak up here and give us a little bit more crust. It's cool, right? Take a moment, just think about how awesome that is, that you're essentially looking at the inside of the earth. Well, it's not cool for these people, obviously. They, I'm sure, are not happy about what's going on, but You know, from an outside looking, it's kind of cool. So, supercontinents. Let's bring this all background, right? We started this conversation, Alfred Wegener and his ideas of Pangea. Let's bring it all around back to supercontinents. Before 2 billion years ago, it's generally thought that you really didn't have large continents. You mainly had island arcs because continents need to form over time, right? But from 2 to 1.8 billion years ago, it's billion, that's a B, it's a lot of zeros, right? These island arcs are swept together by plate motions into a continent. Essentially, you're taking all these plumage events, all this formation going on in the center, like here, all this formation, and you're squishing it all together. When you squish it together, all these individual chains, these archipelagos, if you will, merge together to form continents. And then once they're squished together to form continental crust, now you can have, and again, how they squish together. Well, we see things squished together, like right here. So this is a squishing together. You take these two pieces, you pound them together, you get some mountain forming, things get taller by definition, things like that. You have this formation. Now the continents are there. It's hard to get rid of them necessarily outside of like erosion. So they instead break apart, don't disintegrate, and collide in with other guys. So let's take a moment to talk about the concept of isostasy. I always mispronounce this word. I apologize. Isostasy. Yeah, I think, why not? It'll work. What is this? So we talked a lot about treating the continents as floating things, like floating macaroni in a pot of boiling water. And that's kind of a weird concept, right? It's a continent, but it's floating, right? Continents are huge. Continents are gigantic. How is this thing floating? If I jump up and down, it's not like jumping up and down on a surfboard or something, right? Like jumping up and down on an inner tube. It doesn't go anywhere. What's going on here? Well, funny enough, the continents are literally floating. They have a buoyancy to them because the continents are hard, but the mantle below it is so thick and more dense, it's not going to fall down anymore. So if the continents are floating, and let's say you have a change in the size of the continent, you have a mountain building event, or you have enough erosion to take away a lot of the mountain, take away a lot of the continent. What happens? Well, the lithosphere, the crust itself, actually responds to that change. In the same way that, right, you got a inner tube flowing in the water, you put and you go to sit on, the inner tube sinks down, right? That stuff happens with the lithosphere. This is mostly an impact as shown here of, say, ice buildup, or you can also do erosion, right? The continental crust, as you're noticing here, is being pushed down by the weight of what's on top of it. This all here is a crust that floats at a certain amount. But let's say you have a mountain building event, or in this case, again, ice, something built on top of it. Cities will do this too, to a certain extent, right? You have this dropping of the crust affecting the mantle and the asthenosphere below it. That's really cool. Remember, the mantle, the lithosphere, this stuff's still solid, but the asthenosphere has some flow to it, and you're causing flow reactions by working it this certain way. The idea of isostasy, I keep mispronouncing them, sorry. The idea of this buoyancy of the continents plays a factor in, where am I at? In this whole process. Notice how thick this continent is with these mountains. That thickness is pushing the mantle down here, causing this circling to continue, feeding, if you will, feeding the chain, feeding the effect itself. All these interactions work together, and when you start modeling them on a grand scale, it's quite impressive the way these things work, right? This mountain's getting deeper and deeper, pushing this down, squishing this stuff around, causing these plates to interact with each other. in very exciting ways. So, again, kind of going over things that have already been established, but how does this affect us, right? So what? The continents are floating around, cool beans, what's that mean to me? Well, that magma, right, really hot. When it pokes through something, you get volcanism, usually in divergent zones, but also sometimes in convergent zones. And that magma, well, on the surface, essentially creating new crust, creating new continent, essentially. There are things called large igneous provinces throughout the world that are massive volcanic events that cause the formation of large swaths of crust. Russia has a very large igneous province that is exactly what it sounds like. It's a very large section of Russia that is all igneous rock that exists because of these motions and actions. Well, technically, all the crust exists because of this, but earthquakes would be a thing I alluded to earlier in this lecture. Earthquakes come about from the movement of continents respective to each other. The idea of things, the glue snapping, right? That's just Andreas fault, that's your earthquakes, what have you. Mountain building, which we'll get into in later chapters in more depth, comes from that convergent zone interaction, again, as shown on these images here. If you have two pieces, you got a big piece of paper, a little piece, and a smaller piece of paper, and you run them into each other, the bigger piece of paper is going to buckle, and the little piece of paper is going to slide underneath. That buckling is what we call a mountain building event. And again, it's kind of what you think would happen when this stuff happens. And lastly, migrations of continents and oceans. Things move around, right? Oh, where am I at? There we go. What you're looking at here, think about the stuff that we've talked about so far and picture how this formed, right? This is the result of plates of continents moving around, buckling, and a lot of what you're looking at here is the direct result of what happened underneath the earth. This uplifting of continents, this growing of plates, maybe some volcanism involved, some bunch of forces pushing and pulling. We'll get into stresses and strains here in a bit, and we can see folding and shaping and faulting and fracturing and all these different ways that the rocks get beaten up to form the topography, to form the images that we see in front of us. And then also, this picture shows the end result. Look down here, you got all these valleys, all these cracks and crevices forming from the water flowing. These mountains have been here a while and they're starting to erode away. The material that makes up the mountain is now littering as sediment in the valley down here below it. And that sediment is then growing and forming its own new sediments, forming sandstones, mudstones, what have you. It's all interconnected. This is all a cycle. This is all part of the same game. All right, so I think this is the last slide. Yes, the last slide. I'll probably go into a bit of chapter 7 now because this only took a half hour. But how they affect their surface? Well, all these different continents moving around, all the ways, all the earthquakes, what have you, affect more than just the rocks themselves, right? Ocean and wind currents are very much respond to mountains, deserts, things along those lines. If you have an orogenetic event go on, if you have a mountain building event go on, that's going to prevent wind from flowing. If you have a ocean ridge forming and mountains in the ocean, that's going to affect ocean currents, things along those lines. Glaciation, widespread glaciation is a big component of this. Remember, glaciers push down lithosphere, push down plates. Yeah, a lot of stuff happened. And of course, volcanoes are very destructive to environments. We all are well aware of this. It's kind of cool to stop, think, but you have basically a few mechanisms here, right? You have the convection in the mantle. That convection in the mantle causes the floating lithosphere, the floating plates, to run into each other and move around each other. And that motion causes the Earth to look the way it looks. on a very macro scale. I mean, it can go so far as to, hilly terrain, flat terrain, things along that line, right? Picture America, right? What do you have on both ends? You have mountain range. You have the Rockies in the west. You have the Appalachians in the east. What's the center of America? Very flat. You have flyover states, right? Nebraska, Kansas, what have you. Very, very flat. Why is it very flat in the center, but very mountainous on the edges? Right? And this is a true statement for every one of the continents. The tectonic activity causes the Earth to shape in the way it's shaped. So I think this would be good. I'm going to cut a little bit into chapter 7 just to get a heads up here. And let me switch over screens. There we go. Cool. Let's dive into chapter 7 for just a little bit. Just get our headway in, and then hopefully the next time we have this conversation, we'll be able to finish chapter 7. So let's talk earthquakes and Earth's structure. So, what is an earthquake, right? Before we get into what an earthquake is, we need to discuss deformation. Deformation is a huge factor when it comes to geology, when it comes to understanding the Earth. Within deformation, we have we have 3 main types: elastic, fracturing, and plastic. Plastic and elastic seem kind of similar, but the differences we'll see here in a bit are duly important. Take a moment, think about picture elastic deformation, picture fracturing, picture plastic deformation. What comes to your mind? Because I'm going to give you a hint here, right? This has been prominent throughout the class. What you're picturing is probably pretty accurate. A lot of this stuff is exactly what it sounds like, right? What kind of fracturing does this look? Ooh, give it away a bit. What kind of deformation does this look like? Does this look like something that is elastic? Does that look like a rubber band? I wouldn't say so, right? Is this some sort of plastic deformation? You take a plastic toy, a plastic band, you twist it around a lot. Is that what you got here? No, probably not, right? This kind of look like fracturing. Does it look like something that broke? Well, there you go. When you pictured fracturing deformation in your head, did you picture something breaking like this road? What's going on here, right? Is this fracturing? Are those beautiful swoops in the rock the same deformation that this is? I wouldn't say so, right? That looks very different. Is this elastic or is this plastic? That's a good question. Well, it gives away the answer at the bottom. But is this elastic or is this plastic? Why does this have the shape that it does? And equally importantly, what does that tell us about the surrounding environment? So, an earthquake. Earthquake we can define as a sudden motion or trembling caused by an abrupt release of energy. The amount of energy and the way it's released differs greatly with respect to the earthquakes. Within that idea, we can have slippage and we can have fracturing. Slippage, you could define as a minor movement, a little bit, a slipping, right? Slip. We know what it means to slip. You can slip in some wet water and still catch yourself. If you fracture your leg off of the fall, you probably fell a lot harder, right? You don't slip and fracture your leg, do you? The 2 different actions there. So, we talked a bit before in the last chapter about the different fault zone, different boundary types. Talked convergent, talked divergent, and then lastly we land on strike slip. I told you strike slip is moving in an up and down fashion instead of in towards or away fashion. And this would be an example of this cartoon here. You have the left side of this fault moving, I guess you could say, away from you, and the right side moving towards you. As that movement goes on, the rock doesn't instantly break, because we're generally talking very slow, remember, a few centimeters a year sort of thing. This rock in this picture here, as it's starting to bend, you can see the road bending a little bit with the process. This rock is undergoing what we call stress. It's deforming elastically. If you laid off that pushing, the rock would come back to where it initially was. However, if you keep pushing the rock, eventually you get to the point where it's not going to be able to come back, and it's just going to snap, break off. When it breaks off, all the energy that was holding it in that elastic form is released. This is right. This is the idea of you stretch a rubber band, you stretch it too far, it snaps, slaps you in the face, right? That is exactly the stress and the form that goes on here. This faulting, the road snaps, the power line snap because they overpower the elastic snap back force of the rock, right? Rubber band snaps you in the face if you pull it too hard. That's not the cool part about this, is that's not just a cartoon. We can look at this stuff in real life. Here we have a picture of California's famous San Andreas Fault. Many earthquakes happen in this boundary zone between the Pacific Plate and the North American Plate. This right here, that line running down the center of this picture, is a fault line. It is a separation point between the Pacific Plate on the left and the North American Plate on the right. These two are moving separate from each other, but they're still connected. If you go down in this hole, down in this layer, you're going to walk on rock. That rock has yet to be broken by the movement of the plates, but that rock is still undergoing some sort of stress. What you're looking at is stage 2 right here. Eventually, it's going to snap and give you stage 3 earthquakes. I'm sure I don't need to explain to you that California has its fair share of earthquakes, right? I guess also before I go further, I'm pretty sure they're using this picture because this white line here, is that a river maybe? Or it looks like a road to me. This white road probably was straight when they built it, but this faulting has caused a massive difference in the locations. Right? Look up San Andreas fault lines. You're going to find pictures of farmers' fences being off-put by feet. It's pretty ridiculous. Cool. I'll give 2 mechanisms that can release accumulated elastic energy. Well, that's your braking or your slippage, right? They're not 2 mechanisms really. They're just 2 amounts of energy. But anyways, yeah. All right, so I'll go over earthquake waves. I'll probably call it good for the lecture today. Earthquake waves. Waves are essentially the transmission of energy. Sound waves is the energy that your mouth produces, affecting the air, reaching your eardrums, vibrating like a diaphragm, right? That you produce that energy when you talk. If you clap your hands, you're still producing energy. It takes the energy of your body to bring your hands together. The energy is released as sound, usually, a little bit of heat. Earthquakes follow this very same process. Just if it's a energy that goes through a rock, we call that a seismic wave. It's the exact same thing as talking or blowing air or clapping. It's all the same basic physics. Seismology is the name we give to the study of the seismic waves and the things that produce them and what those seismic waves tell us. Very useful, very super useful information for all sorts of different aspects of geology and the economy. We're going to focus a bit more on the earthquake side of things for this particular chapter. So, now that we understand seismic waves and energy, a couple key terms for earthquakes. First one here is the focus. The focus is the rupture point where the energy is released. That snapping going on, that snap point right here, that would be the focus. In this example, the focus is on the very top, but usually this is the energy is released down here below at some point. That is what we call the focus, the location where the energy is released. And then from that, we can find an epicenter, which is essentially the point on the Earth's surface above the focus. If the energy that caused this fault line here was some, 1,000 feet below the Earth's surface, then the epicenter would be right at this edge here. And it says focus and epicenter like it's a distinct singular location. That's not usually how it goes. The focus is usually a plane. Focus is usually a long strip where the rock broke. And again, the same thing with the epicenter. We tend to simplify it into a spot because it makes explaining what's going on easier. And it's not going to benefit people when you talk about earthquakes to say this, this plane bisects at this angle is not necessary, right? So you have two different blocks that we call them here. We have this block on top and this block down below. I'll get into nomenclature of naming of these things in a bit. But a force caused this block here to move. Or maybe this block here to move. I can only tell by looking at this which one, if this went up or this went down. But actually, no, arrows, hey, look at that. You have these blocks were at one point level. This above ground was level. Something caused either this block to move down or this block to move up. And when that happened, all the rock along this red line here faulted. All the rock along that red line either slipped down or slipped up according to the motion that happened at this particular event. We tend to define a particular location where the most energy was released as the focus point. And it's more than acceptable to do it that way, right? Sure, along this fault line, many different places popped, but we're going to centralize it for sake of conversation to a focus. And then you draw a line to the top of that focus to the top here, you get the epicenter. The epicenter is important because the epicenter is what affects us as people. As I'm sure you can imagine, the closer you are to the earthquake, the more power you have because the energy has to ripple through the earth as it travels, and when it ripples through, it loses some of its energy in the process of moving. So the closer you are to the epicenter, the more dangerous it is because the epicenter relates directly to the focus of all the energy released by the earthquake. Hope that makes sense. A lot more involved with that. We'll get into some of it, but that's focus, that's epicenter. How does energy travel through? Well, again, let's go back to some basic physics here. What type of waves are there that exist? I'm sure in some high school science class, your physics teacher or your earth science teacher physical science teacher brought out a slinky and had you play with slinkies, right? Super fun. Yeah, you probably broke them because that's what high schoolers do and middle schoolers do. But he had you treat these slinkies in two ways. The first way he had you treat the slinky was he had you grab a piece of it and pull it directly to your hand and release it, right? When he did that, you created what's called a P wave or a compressional wave, as shown here. The energy travels in the same direction as the object, in this case, the slinky. This is a compressional wave or a P wave as we refer to it in seismology. The other thing he might have had you do is he had to hold that slinky, take a piece and pull it perpendicular, pull it out and then snap it, creating that like wave pattern as it travels. This is an S wave or a shear wave, wherein the force, the way the energy travels along the rope is perpendicular to the force on the rope, which was, in this case, up-down, right? The ant goes up, the ant goes down. Whereas in this example, the ant goes forward and the ant goes back relative to the slinky. These rocks do these exact same things because, again, energy is just waves are just moving of energy, and the way that the waves move affect what's going on here. When you get to the surface, you can have rolling waves, and it's kind of the same process, just it doesn't move as fast because you have to buckle the surface instead just go through solid rock. But again, you can have your shear wave giving you your classic earthquake coming in, and the ground is flying around all cartoon-like. That's exactly what happens. Again, I'm just going to have to ask you to think about 8th grade, 9th grade science and your teacher pulling off the slinky for these examples. but I imagine most of us at this point of the game pretty understood these different types of waves. So, distinctly, let's bring this back to seismology. Let's bring this back to working with the rocks. We can imagine initially these rocks had this description to them at the end. They were all cubes stacked up in a big long collection like that. If you shove a P wave through that, you shove a compressional wave through that, what happens is you have an extension and a compression of these squares as a result of the energy rolling through it. Some of these squares will squish together. Some of these squares will expand apart as the wave rolls through here. And we're not going to get into a wavelength and stuff like that too much, but you can tell the size of the wave and the rocks adjust accordingly. You can imagine literally the rocks bending and squishing as the energy flows through it, and probably damage of some sort, right? The S wave, conversely, is up and down motion or side to side motion, but it's the same basic process. Notice here, however, that the rocks aren't being squished and expanded. Instead, the rocks are being distorted by shape, but keeping relatively the same amount of the same basic shape, right? They are not, I guess you could say, the same area or the same volume. It's just they're getting this nice wavy pattern instead of being squished and being fanned, right? You take this exact same idea of the P and the S wave, but instead this essentially would be inside of the rock, and right here we actually have a surface of a rock, and this is the part that you walk on for the Love and Raleigh waves. Other than that, you're talking essentially the same concept here. The Raleigh wave looks a lot like the S wave because they're kind of the same thing. Love wave is essentially a version of the P wave, although I guess a better way to put that would be the love wave would just be the left-right motion, or the Raleigh wave would be the up-down motion. I think that'd probably be a better way to describe it. But yeah, that is how these physical mechanisms work when you have energy transferring through them. And again, this is kind of exactly what you would expect it to be. The weird part is wrapping your head around a rock acting this way. But you got to go back to your basics of physics. How do you transfer energy? These two ways, either parallel or perpendicular to the direction of the motion. We get these P waves, these S waves traveling in this exact same format. Super interesting, right? I don't know. I guess it's kind of a slideshow. You can only do so much, right? My suggestion to you, if this is confusing to you at all, if this is you find this explanation a bit lacking, YouTube it. YouTube P wave, YouTube S wave. You can probably find images and videos of this stuff in action. But what they're probably going to end up doing is, again, showing you a slinky and saying that's how it works. So we know how energy travels through rock. How do we measure that? Earthquake seismologists use something called a seismograph. A seismograph, shown here a super rudimentary version, essentially draws the shaking or the movement of whatever you're walking on. These can be super, super, super sensitive, down to the catching your feet as you're walking across the ground. Because again, those vibrations are a movement of the rock. The rocks will always move. They're not going to move a whole lot, but they will move, causing these vibrations. This is, of course, a bit exaggerated. This would be a massive volcano to cause the ground to move this much, right? But that's a seismograph. And this roll here, this piece of paper, you've seen these images before, right? These images here, these are called seismograms. They're paid by seismographs, right? Okay, I guess I gotta say that now. This information is useful because, as you can imagine, right? Like here at rest, the ground moves up a little bit, you get a little drop. The ground moves a lot, you get a big drop. The amount of motion on that seismogram amount of motion here on that seismogram tells you essentially how much energy has been released. We use the Richter scale to define earthquakes by energy release. Moment magnitude is a bit better, but get to that. And what the Richter scale does is it ties back very nicely into this image here. Because as we said, as you leave the focus, as you leave the epicenter, you go through more material, the energy is used up in this process. The energy is being transferred, being moved, but the further away you get, the less energy there is. So a Richter scale or a moment magnitude scale, which is a better use of the measurement of energy, essentially tells you how close the earthquake was and how big the earthquake's energy release was, right? A slippage versus fracture comparison. You could be right next to a small earthquake, or you could be really far away from a big earthquake, and you could achieve essentially the same amount of energy in those two examples. The Mercalli scale, the one shown up top here, doesn't care necessarily about the size of the earthquake. It instead compares about the damage caused by that earthquake, meaning buildings collapsing, fires being set, loss of life, things like that. The Mercalli scale very much cares about how close a person is to the earthquake, more so than the size of the earthquake. A relatively small earthquake, if this earthquake right here is really small, but the town is at that letter N, you're going to have a very large earthquake in the Mercalli scale because a lot of damage can be done. However, if this is a really big earthquake, but the town exists way up here, the wood figures the town far enough away to feel the earthquake but not cause a lot of damage, very small Mercalli scale. So let's get into this guy. What's a seismogram? What does it look like? Funny enough, PS and the Love Rayleigh waves all interact differently with the Earth. Given the way that the energy is moved through the medium of rock, P waves actually travel very fast. P waves exist only within the rock, as shown here within this rectangle of rock. That's the only thing that's being affected by that energy. So the P wave moves very fast. If you get an earthquake, the first thing you see is the P wave, or I think sometimes you call them primary waves for that exact purpose. These rocks here, these S waves, these shear waves, or these examples, secondary waves, reflect a slower transfer of the energy in a different medium. Again, you can imagine the amount of energy it takes to push this rock up when there's rock on top of it. You shove in more rock around to achieve the same flow of energy. So that perpendicular motion, as opposed to parallel motion, arrives a bit later, but it's noticeable because it's the same quantity of energy shown here. Your primary wave and your secondary wave. And then we have to remember these seismographs tend to sit on something. That's how they work, right? So when the top of the earthquake starts buckling around, when the top of the ground starts buckling around to the earthquake, then your big dude shows up, and we call those your surface waves. And down here, and usually this isn't really scaled up to down. Well, I mean, it can be, but it depends on what you're doing, right? But this isn't necessarily a particular amount of energy because, again, to go back to the different scales here, the energy release of an earthquake has as much to do with the earthquake as the distance away. So you could have a massive release of energy here, right? There's been huge earthquakes all over the world, but if you're far enough away, you don't notice it. The earthquake that flooded, I think, Indonesia, right? Like 2010, 2009, something like that. There was an earthquake that caused a tsunami that crashed over and destroyed all those islands. We didn't feel that in America, right? Because we were so far away from them. The earthquake was felt by seismograms. You can go to any place that has seismograms of them, and they should probably have a printout of the, I think it was 2009 earthquake. But again, the key factor here is the energy release that you feel is not indicative of the total energy of the earthquake release, instead indicative of the earthquake energy that only got to you. So the more important thing arguably is the time scale. And we'll get to time scale when we get to talking about locations of earthquakes. I think this is probably a good time to pause. The assignment I gave you involves locating earthquakes. If you would like to see more of this lecture than just right now, send me an email, comment down below, check Canvas or whatever program we're using when you watch this, and I can give you the slideshow if you want to skip ahead a bit in the lecture. That being said, as I always try to indicate to you, it is very, very wise to find other sources that can help elicit a better understanding of what's going on here. There's lots of good, high-quality information on earthquakes I suggest you look up if you need it. That being said, you will find this stuff too, like with all geology, be very forthright and very easily understood, for lack of a better term. The way energy travels in an earthquake is the same way that you learned about energy traveling with a slinky in 8th grade or 9th grade, something like that. The way a seismogram works, these things are produced kind of how it says. This was a needle. This is a needle that is directly affected by the movement of the earth. So that needle jumped up and down because the earth jumped up and down. Very interesting stuff. We'll talk about locating earthquakes next lecture. Thanks for coming by. Drop a comment below if you have any questions. I'll try to get to them as best I can. And thanks. Stay safe out there.